This video is an overview of partial fractions. Our goal is to rewrite a rational function as a sum of simpler fractions. What I want you to get out of this video is the knowledge of when to use partial fractions, the forms for partial fraction decomposition, specifically how to write the numerator, and finally how to solve for coefficients. Partial fractions can only be used when the degree of the numerator is smaller than the degree of the denominator. If the degree of the numerator is larger than the degree of the denominator, you must use polynomial division first. There are other videos available on that topic. This table will help you write the correct partial fraction based on the form of the factors in the denominator. First, make sure the denominator is fully factored. Linear factors have the form ax plus b, or simply x plus b, or simply x. A linear factor needs a coefficient in the numerator that is just a constant. We can use the letter a, and then the partial fraction would look like a over little ax plus b. Repeated linear factors are when you have a linear factor that shows up multiple times, such as ax plus b quantities squared. Each linear factor needs a constant in the numerator, so we could use a, b, c, or d for example. The partial fractions are then written out with a fraction for every instance of the repeated factor. So we would need an a over ax plus b and a b over ax plus b quantity squared. Irreducible quadratic forms have a quadratic in the denominator that cannot be factored any further. Irreducible quadratic factors need a linear numerator, so we could use ax plus b, and then the partial fraction would be written as ax plus b over whatever your quadratic factor is. Note you can also have repeated irreducible quadratics. For any repeated factor, there will be a partial fraction for every power of that factor. The final step is to solve for the coefficients. So let's say we have this example. We have a linear factor, so we can give a coefficient of a. We have a repeated linear factor, so a coefficient of b. And then we have an irreducible quadratic, so we need a linear factor on top, so we could use cx plus d. Our next step is to multiply through by the denominator on the left side, which will allow us to clear the fractions. Notice this is similar to finding a common denominator. Because the a part already has an x plus 3 in the bottom, we only need to multiply by 1x plus 3 and the 4x squared plus 1. The other x plus 3 cancels out. Likewise with the b, the x plus 3 squareds cancel out. And with the cx plus d term, we just need to multiply by the x plus 3 quantity squared. Next, work through all the algebra to fully expand everything on the right-hand side, and then group by like terms. Once we have the completed expansion, we can start pairing up coefficients on each side of the equation. So we look for the x cubed terms, look for all the x squareds, look for all the x's, and look for all the constant terms. Let's pair the coefficients. On the left-hand side, we notice there is no term with an x cubed, so we just write a 0 for the left-hand side. On the right-hand side, the coefficient in front of x cubed is 4a plus c. Looking at the x squared terms, on the left-hand side, we notice there's a 3. On the right-hand side, we have 12a plus 4b plus 6c plus d. Collecting the linear coefficients, 2 from the left-hand side, a plus 9c plus 6d from the right-hand side. And lastly, collecting the constants, we have a 10 on the left-hand side and the 3a plus b plus 9d on the right-hand side. This gives you a system of equations that you can use to solve for the coefficients. Note that if you only have linear and repeated linear factors, there is a shortcut that is outlined in another video. Once you have found your values for a, b, c, and d, simply plug them in, and you will have your partial fraction decomposition.